Okay, recording is rolling. So welcome to Wednesday, December 1st. And I have a torque lab for you guys. It's going to take all class periods. So I'll show you guys the setup here in the first few minutes, and then you guys on your way. Right, so you guys see this meter stick hanging from the ceiling, a couple of spring scales. Looks a lot like this picture. Even the lab weight in the middle, so it looks a lot like this, right? And this is just a copy paste of it right here. Right, now, I'm going to have you guys measure, well, you have a goal with this torque lab. Just trying to figure out the best way to put a torque lab together. And the goal I have for you guys, if you see right here, I zoomed in, so it says mystery scale reading, right? Mystery scale reading, right? So that's the goal, and that's going to refer to this scale right here. Like, suppose you were able to measure everything except for that. Maybe it's like a broken scale, so maybe it can hold some weight. You know, the spring's broken, but maybe the scale, the numbers are rubbed off or something. Okay? And you're trying to figure out, I wonder what this force reading is. Hey, maybe I can calculate it if I know that the torque has to sum to zero. Right? Guys get that? Right. Now, uh, notice that the pivot point is defined at the 0 centimeter mark. Right? Is that? Which is maybe like this point right here. So I'm going to label this point the pivot point. Right? Now that's a really kind of abstract idea because there's nothing really physical going on there. I mean, there's no like physical door hinge or anything, even though you're thinking of it sort of that way. But from this pivot point, do you guys see that this left scale is pulling up with some force that's going to cause well, again, from the point of view of this pivot point, again, kind of abstract idea, this would be causing a counterclockwise torque. You guys see that? Counterclockwise torque? Right? The meter stick itself has a weight, and you're going to treat the weight of the meter stick acting at the center of mass of the meter stick, which is about the 50 centimeter mark. That looks like it's going to cause a small clockwise torque. The lab weight itself is going to cause a clockwise torque. And this mystery force over here, suppose you don't know what it would be, although obviously you could just glance at it and see what it is. Right? Anyway, it has an upward force, which is going to cause a counterclockwise torque. Okay? And don't these four torques have to sum to zero? Right? Sum to zero? Right? That's pretty much the premise. Right, now, run down to these numbers. Right, so forces are going to be measured in newtons, and I've got distances in centimeters. Now, if it's a classic textbook type question, usually it's forces in newtons and distance in meters, but we're going to do centimeters. Right? But speaking of force in newtons, a lot of the values that you can grab right away would actually be mass values in grams. So think about how you could convert that over to newtons. Like, for example, suppose this is one of your lab weights, okay? And it's got a number stamped in it. It says 500 grams. That's 500 grams. Does anybody remember about how many newtons this weighs? Yeah, about 5 newtons. In fact, if you want to call it 5 newtons, you can. If you want to be a bit more accurate, here, let me take you guys through the process. Okay? So I'm going to take the 500 grams, whatever the grams numbers is. Okay? You can also use this process for like the meter stick and other numbers later. How do you convert from grams to kilograms? Divide by 1,000. Okay. And then to go from, so this would be the mass in kilograms, right? So this is half of a kilogram. Okay. Then to go from mass in kilograms to weight in newtons, you just multiply by
10.
Yeah, about 10 meters per second squared. Right. So 0.5 times 10 would be, that is the 5 newtons that you guys said. And tell you what, if you want to be a bit more accurate and call it 9.8, you can. I'll leave it up to you, whether you want to use 9.8 meters per second squared or 10 meters per second squared for the gravity field at the surface of Earth. Okay. So a little bit more strictly, this is like 4.9 newtons of weight, right, at the surface of Earth, right? The planet we're on. The meter stick itself, you can measure using a triple beam balance. I'll tell you guys, if it's a blank meter stick with nothing on it, it's about 70 or 80 grams, somewhere there. So then go through the same process, like 80 grams, for example, divide by 1,000 times 10, that'd be about, it should be in the vicinity of about a Newton, right? Now, if it has a bunch of metal clips on it, like this one hanging from my ceiling, that's gonna possibly up to double the mass. So anyway, the meter stick, whether it has the metal clips on it or not, should be in the vicinity of about a Newton of weight. Okay. Also remember that these are vector values, so positive, negative directions. The meter stick has a weight that's acting downwards. This hanging weight is acting downwards. The spring scales are pulling upwards, so somebody has to be negative, right? There has to be a negative sign somewhere, right? And same story with the torques, whether it's clockwise or counterclockwise, have positive and negative torques. Right? But at some point in the process, all these torques have to sum to zero. If you add these all up, they have to sum to zero, right? Now, 3 of them you can get from your calculations, and then this mystery force is causing this mystery torque. But whatever this is, this has to be the opposite number so it balances out to 0, right? And then you can follow these flowchart arrows, and if you know torque is r cross f, and you can calculate the torque, and you know its location, this radial arm, could you guys divide and calculate what the force has to be, right? And then, good. So now we're at the end of this process. So at this point, you would have calculated what the force should be. Hey, look, force sub right, the force on that right scale. But then you can just measure it, right? You can just like get a straight reading. And these two numbers should ideally be the same, or maybe like pretty close to each other, right? They might be like 5 newtons and 5 newtons, something like that. Okay? All right, so that's a quick rundown there. Now, what's the deal with the right side of this paper? Because if you look at the diagrams, see how the diagrams look exactly the same? Right? In fact, you know what? You could use the exact same setup. So, right, same setup. You don't have to change anything from the left picture to the right picture. You could use the exact same setup. Okay? But what I've changed is it's not even your goal of change. You're still solving for the mystery scale reading, which is the force on the right. Right? So that's the same. What I've changed, though, is the definition of the pivot point. See where it says pivot point is where the left force is located? Okay. That's referring to this point right here as the pivot point. Remember, you can technically pick any point as the pivot point, and the torque should sum to 0. Okay? But that's the only difference between the left side and the right side. Is just where the pivot point is. Okay? Now, actually putting the pivot point here probably intuitively makes more sense, because that literally could be a pivot point. Right? Say if you took the spring scale, start moving up and down, it could actually start pivoting about that point, couldn't it? Did you guys imagine that? Right? But mathematically, there's an extra step you have to throw in there, which is that to calculate each of these radial arms, you have to subtract the distance to that point. Okay? But on the other hand, the force itself at that point doesn't cause any torque about that point because it's at that point. Kind of like if you push on the door hinges of the door, it's never going to turn the door. Okay? So the meter stick itself has some weight, causing a clockwise torque about that point. The lab weight, clockwise torque, and the mystery force, counterclockwise torque. Right? But remember, the lever arms are going to be relative to that location. So whatever the distance is in centimeters, subtract the location of the left force, and then get these radial arms. Guess it? Right? So then, similar thought process, torque should sum to 0. You can back calculate what the force had to have been, then get a direct reading. It should be like 5 newtons, something like that. Okay? All right, so that's one setup. This is the setup that, again, looks a lot like the one that's hanging from my ceiling. Looks a lot like this picture. Okay? On the back side of this page is a different looking picture. You guys see there's just one spring scale holding up like 2 weights. Ooh, that's kind of like the opposite process, isn't it? Right? And your goal here is to solve for the mystery lab weight. Right. Suppose you didn't know what this lab weight was. I've used this exact process to, I remember way back in the day I was teaching, I pulled some lab weight out of the closet that didn't even have a number stamped on it. And all the digital scales were broken. And I actually used this exact method pretty much to solve for it. I remember, funny story too, I remember it was 67 grams. And I thought that had to have been a mistake, because who would make a lab weight that's 67 grams? But I did get hold of a digital scale on, it was 67 grams. So I was like, that's worked out. But yeah, that's what you guys get to do there. Right? So this is the perspective, again, about the 0 centimeter mark, which is like right here. So here's your pivot point. Right? Let me do this. Right. Slide over here, very similar to what was on the other side of the page. It's the same goal. You're still also solving for this, but I'm just going to change the perspective to the point of the scale, right? As the third point. So back here. All right. So from the left point, each of these locations actually would represent the radial arm from that point. And this is kind of an abstract idea, because what's going on at 0 centimeters? Well, nothing really, right? But clockwise torque, counterclockwise torque. Make sure you got some negative sign somewhere, and then a clockwise torque. Right? And if you sum all the torques, they should sum to 0. Therefore, there should be enough information that you can calculate what the that force should be, and then get the direct reading, and these should be the same. Okay. Right. And then just again, this could be the same setup. I'll even write same setup. Okay. But switching perspective, What if you call this your pivot point? Just change the definition of what the pivot point is. Okay? Well, this one's probably more intuitive because I could totally see this, these, like swinging like this, right? Okay. Now, you want to balance it so it's in equilibrium. You might have to shift some weights around to get a balance point, but then you just keep your setup. Okay. From this point of view, pivot point, do you guys see this radial arm for the weight causing a counterclockwise torque? This radial arm to the center mass of the meter stick causing counterclockwise torque on my picture. Okay? And then the mystery weight would be causing a clockwise torque. Okay? And those three torques should sum to 0. Okay? Okay? And then you can calculate what the force had to have been to for all that to happen. Okay? I do want to mention too, there is a triple beam balance back there that you can use to grab the masses of things. So if you want to measure what's the mass of this meter stick, so you can get like an accurate reading, you can do that. And the triple beam balance, triple beam balance. Actually works on exactly this principle too. If you think about like how that would actually work, so it's actually pretty similar to that. All right. So you guys got all class period to do that. We're just gonna have to do 1 lab page per group because that's my printing budget, and then you guys can turn this into the gray shake by the end of class. Walk around, help you guys out.